Hi students, this lecture is for the 25th of March. This is Friday, and as a couple of announcement reminders, remember that next week we have an exam, and so what that means for the homework is that you've got until Tuesday the 29th to submit that, and it should be uploaded to Blackboard before 1 p.m. And then at 1 p.m. the solution for that will be visible on Blackboard, and then the following day, on Wednesday the 30th, is when we're going to have our second midterm exam. And for that midterm exam, it's all of the material since the first exam. You're allowed to bring in 1 page of notes, front and back, on a letter-sized piece of paper. And then I'm going to be providing that same formula sheet that I gave you during the first exam. This lecture is going to address phase 3 of the project, and so I'm going to give you an illustration and some information on how you can size the reservoir for the project. And then we're also going to do a little bit more work with the specific energy equation and see how that can help us to find the new flow depth when we've got a channel constriction, like when some piers are put into a river. All right, so the bulk of this lecture has been recorded in a previous semester, therefore there may be some questions from other students or incidental references to times or dates that don't quite match up, but all of the material is the same. And if you do have any questions about the announcements or the material itself, please feel free to get in touch. I regret that I've got a meeting today that will keep me out of class, but I am still available on Teams in the afternoon and in the morning if you have any questions. And of course, you can contact me over the weekend as well if you need any help on the homework. So let's get into the lecture.
We have a reservoir in the project because we want to, number one, pressurize the network. You can pressurize a drinking water distribution network with pumps, of course, and in a lot of flat places that's how they pressurize the water network, is just to have a pump operating at all times, and that adds pressure and the water can be withdrawn from people's faucets. And the other way to do that, though, without requiring any electricity, is to have an elevated storage tank. And so if you have a tank that's lifted up high enough, then that can pressurize the network, or at the very least it can reduce the size of the pump that's needed or how often the pump is required. And in our project, what we're trying to do is achieve the pressure in between 240 and 850 kilopascals. And remember that this design condition that you've been planning on isn't going to be a very frequent occurrence. Think about what's happening during the design. You've got all of your maximum residential demand at the same time as all of your maximum commercial demand. We're assuming that there may be a fire occurring at the same time. The food processing plant is operational. They're irrigating the grass at the golf course. The hospital is at peak demand for its water. The high-density housing is at peak demand for the water. The box factory is operational. So the sports stadium is having its halftime for whatever the event is. Just to ensure resilience of our system, we have to size it so that all of those demands could occur simultaneously, and we're still able to provide the needed volume of water at the minimum acceptable pressure. But that's not very often. Most of the time the demands will be much lower, and so we're going to be closer to this maximum pressure. And the maximum pressure is going to be observed during periods of low flow or no flow, like the static condition at night. So we want to pick a reservoir location that satisfies both of those constraints. Now, another reason for the reservoir, besides it's the source of pressure, is it allows us to meet the demands that are variable with the supply that is constant. Now, in this project, I've told you that the water is coming from a spring up at the top of the hill. If you look at the map, there's a 300 referring to the elevation contour lines. The spring for our project is near that location. There's a little symbol on the map, but it could be the same situation instead of a spring if it was a water treatment plant. the chemical process that is used and physical process that is used to clean up water from a river and turn it into something drinkable, you can't turn it up and turn it down with instantaneous response. Those systems are far more efficient when they operate at a steady state, or as close to a steady state as is possible. So part of the reason why we have this reservoir or tanks that store finished fresh water is to make sure that during these periods of high flow demand that we have enough water at the ready to supply the demands. So we may have water coming in at a constant rate and then it's coming out of the reservoir at a variable rate. So we're going to figure out, I'm going to give a demonstration for you today that illustrates how large the tank should be. Now, I've provided this curve in the past on a homework assignment and asked that you digitize it, meaning for every hour of the day, go over here to the vertical axis and then just read the number associated with this larger curve. So the maximum day for the year, this is showing just the temporal variation. Temporal distribution just means how something varies over time. And so what we are seeing is that there's some maximum for the day, and we know from your demand estimation summary sheet, at the very bottom of that summary page I asked you to write all your numbers on, at the very bottom it says what's the demand for the whole network. And we're saying, by definition, we're going to tie this curve to that peak. So it maybe is 200 liters per second for your city, or maybe somebody else's city is 300 liters per second, or 350 or 400. You know, everybody had different assumptions that were assigned for the project, and so everyone's going to have a different maximum outflow for the network. But for each case, we're saying, let's tie that peak demand to this point on the curve, and you'll notice this is a linear scale, and so if we're saying this is 400 liters per second, and that corresponds to 275% of the average day, then we could find out, if this is 400, we can find out how much water demand there is at midnight. It would just be a ratio. It would be 100 divided by 275 multiplied by our maximum demand of 400. And so what we can do for every hour of the day is use the shape of this curve to find the outflow from the reservoir. So this curve defines how much water is coming out of the reservoir and going to the town. If we wanted to know the flow into the reservoir, in a 24-hour period, let's assume that the flow in equals the flow out of the reservoir. Now this is a really important idea. This is an application of the continuity principle, and what we're saying is that during a 24-hour cycle, the flow into the tank and the flow out of the tank is the same. We're going to put enough volume into that reservoir that at night it fills up, and during the day, when there's a high demand in the city, the tank is going to drain. And the reason why is that during the day, there's more flow coming out of the tank because of those really high demands than there is flow coming in. So this blue line represents the balance in a 24-hour cycle of the inflow versus the outflow. And so the area under the curve represents the volume of water that's being stored, and the area above the curve represents the volume of water that is going to be drawn out of the reservoir during high flow times to supplement the average flow that's coming in. So I think that this concept maybe will make more sense as we actually go through the spreadsheet, but the important thing to keep in mind is that we're going to design this storage tank so it's big enough for the biggest day of our expected design life. You know, 20 years in the future, when the town is all fully developed and it's having this peak demand experience, we want to make sure that the reservoir is large enough so that the city doesn't run out of water. Okay, now this is my attempt to digitize the curve. You use your data, but just for purposes of illustration, this percent of peak is what I'm going to be showing when we open up Excel. So the percent of peak is just me taking this percent of average day and dividing it by 274. Boy, it looks like I was really precise there. I said that was 8 p.m. is 274%. 7 p.m. 273%, and so on. So 8 p.m. is 100% of the peak because that's the highest point of the day. But then if we look at midnight, midnight is 100% divided by 274. So here at midnight it is 57% of the peak. So don't get thrown off by the different percents that we're dealing with. There's the percent of the average day. We're not designing for the average day. We're designing for the peak day. So we want to know, how does this curve describe the percent of the peak day? All right. Now feel free to interject. You all have microphones on your computer. Don't be ashamed or shy to unmute yourself and ask a question as I'm going through this demonstration if there's something that doesn't make sense. All right? In fact, I'd love that. So I'm going to copy and paste this table into Excel. So Control-C for copy. And let me start a fresh worksheet here. And I'm going to do Control-V just to paste. What you'll do is use the data that you developed earlier in that homework assignment where I asked you to digitize the curve. All right. I'm going to put in a couple of extra columns though. I need to open up some space because there's some other things I'm going to calculate. So first of all, let me put in a couple of extra rows just so we have some room at the top, and then a couple of more columns so that I've got some room in between. All right. Now, we're starting here at midnight and going through 11 p.m. Each row represents 1 hour. So this row represents from midnight until 1 a.m. or until 12:59:59. And then at 1 a.m., this is our flow out percentage. Okay, now what we know is our max flow. We're going to do this example with the following data. We're going to do an example where we'll assume our peak demand is 400 liters per second. In your project, you had some other peak demand at the bottom of your summary sheet. But just for purposes of illustration, I'm going to use 400 liters per second to figure out how big should the reservoir be. All right, so up here I'm going to say max flow in liters per second is 400. And let me just, that, okay. So if that is the maximum outflow, then next to this I'm going to have my flow rate out, and this is going to be in terms of liters per second as well. Okay, so the flow rate out is the max flow, which I'll anchor, multiplied by the percent of peak. And so now look, what we know is that the flow rate out is highest here at 8 p.m. So according to the curve, I'm saying I want 400 liters per second to be at 8 p.m. And so I've used that curve to tell me what's the flow rate out at all the other times of the day, because they're some fraction of the peak. So hopefully you see how I've just used this percent of peak table. What I've done is I've multiplied the known outflow by the percent of peak. Okay. Now, I'd like to know what is the average of this during the day. I know that the highest point of the day, it's 400 liters per second, and I know for every hour what's the flow rate, but let me find the average flow out in liters per second. Okay, so I've got all this data equals average 253.5. Okay, 253.5 liters per second is the average flow out of the tank. Now the reason why I want to know the average is because the flow into the tank in a 24-hour cycle is going to be equal to the average flow out. If that wasn't the case, then there wouldn't be balance between the inflow and the outflow. Like if I had more flow going out during the 24-hour cycle than is going in, then that means that the tank is going to run dry before the end of the cycle. So I'm going to say that the flow rate into the tank is this average flow out. So I'm going to set it equal to 253.5. Oh, and I've got it formatted as time, which I don't want. I need to format that as a number. Okay. And I guess I'll anchor the reference so that I can drag this down, and it's always looking at the average flow out. So that's the flow rate in, and here's the flow rate out. So let's think about what I'm going to call ds dt. Well, before we do that, we can calculate the volumes, but at midnight there's more flow in than flow out, so that means at midnight the tank is filling. At 1 a.m. there's more flow in than there is flow out, so that also means the tank is filling. But think about what's happening at 8 a.m. No, even at 7 a.m. it's happening. There's more flow out than there is in. So at 7 o'clock it's going through this transition where the tank is going to begin emptying because there's more flow out than in. So anytime this curve is above the line, that means the tank is draining. And then anytime this curve is below the line, that means the tank is filling. Okay? So we know the flow rate in. Let's calculate the volume in during the hour and calculate it in terms of cubic meters. Volume in during the hour, because each row represents a 1 hour period. So if it's 253.5 liters per second that's coming into the tank, anybody know how many seconds there are in an hour? Type it into the chat box if you do. It'll prove that this is an interactive class. There it goes. Harrison's got it. Isaiah's got it. 3,600. Good. Okay, so the volume in during the hour is going to be the flow rate multiplied by 3,600. So that is formatted as time, which isn't great. This is liters per hour, but I want to divide by 1,000 to get cubic meters per hour. Okay, so if we have 253.5 liters per second for a 1 hour increment, then that means that there's 912.6 cubic meters during the hour flowing into the tank. And that's the same for every hour because, remember, the inflow is constant. In this project, we're assuming that the spring, the water is trickling from the spring towards the tank at a constant rate through the day. And if it was a water treatment plant, then this would be the rate that we are taking water from the water treatment plant and then the hourly volume. So that's in. Now let's think about the volume out. Okay, this isn't going to be the same every hour because our flow rate out is changing for each hour. So the volume out would be the flow rate out multiplied by 3,600 seconds per hour divided by 1,000 liters per cubic meter. Okay, so that tells us how many cubic meters are flowing out of the reservoir during the 1 hour increment. And I can, let's see, you drag that down through. And so it tells me for each hour what's happening for the flow out. And now ds dt. This is what is the net accumulation in the reservoir during the hour. So from 12 to 1 a.m. here in this row, in volume minus out volume is positive. So that means during the 12 o'clock hour, 394 cubic meters of water was stored in the tank because more came in than went out. And for each hour of the day, we can see that sometimes there's more water coming in, sometimes there's more water coming out. By the way, since we're on the subject of spreadsheets, let me ask you, what do you think looks better? This, or is it better to do this? Is that more fancy if we put a lot of extra zeros at the end? It's silly, right? It just kind of makes it visually distracting and cluttered. It doesn't add any value. So don't display insignificant figures in a spreadsheet. It's better just to have it be simpler, and if there is any precision, it will stay there even if you're not displaying it. So we can have it display it to the nearest liter per second, but even if it has fractions, they'll still be there if they aren't displayed. Sometimes I see spreadsheets that has, like 12 significant digits, and it's clutter. So I wanted to make that point before I forgot. All right, so now this is an important part. We want to know in the evening, so look at 7 p.m., 8 p.m., 9 p.m. Okay, we have a lot of demand in the evening. Our peak is around 7, 8 p.m. We want to know when in that evening time does the tank just begin to fill, because we have to start this daily cycle analysis with the assumption that the tank is empty and just starting to fill. So you'll notice it's here at 11 p.m. that for the first time in the evening we have a positive ds dt. At 10 p.m. there was more flow out, which means the tank is still emptying. It's almost through its daily cycle. There's just a little bit of water left in the tank at 10 p.m. But then at 11 it starts to fill. This is a really important point. When students make a mistake on the project for this phase, it's usually they forgot this part. It's not complicated, it's just important. So what I'm going to do is I'm going to move the 11 o'clock hour to the top. I'm inserting an extra row there. I want the daily cycle to begin with the hour that the reservoir just started to fill. So I'm moving this up to the top. Now I have to make sure that it doesn't change my average flow rate. If the average formula is looking in the wrong spot, I'm going to have to readjust that. But I'm moving 11 p.m. to the top of the list. It changed it. So let me just make sure here the average refers to the whole day. Okay, I fixed that there. So what I did, and the reason why, I put the 11 o'clock hour at the top because that is the first hour of the day, of the evening, that the tank starts to fill. So I'm assuming that 11 o'clock is when the tank is just about empty. There's just a few drops of water in there, but then at 11 it begins to fill again. Okay, last column, accumulated storage volume in cubic meters. Okay, accumulation. Just to make this a little narrower, let me wrap text here, and then that will allow me to do this. Alright, so accumulated storage volume. At 11, the tank was empty, but then it just started filling, right? So the volume of water in the tank during the first hour is just how much came in during that hour. But in the second hour, it is the previous hour's accumulated volume plus how much new flow came in during that hour. So it's the cell above and the cell to the left for the accumulated storage volume. Now I can distribute that formula downward. So if I do that to the next row, what it's doing is it's looking above at the previous accumulated volume and how much new water came in. Okay, if I do that through the night, it keeps going up and up, but then in the morning, when we've got a lot of flow, it starts going down again. So here's what we want to make sure. We want to make sure that this cycle ends at 0. If it does, then that tells us by the end of the day we use up all of the water that's in the reservoir. And so the required volume that we have to have is the biggest of these. So let's just do a conditional formatting here to draw attention to the largest of them. I'll do conditional formatting. I want to highlight the top one value by making it bold. Conditional formatting isn't the essence of this project, but it's this one. You could have just looked at it and seen this is the maximum storage volume required. Just for a safety factor, what I would do is I would size, the tank that actually gets built, maybe I'd make it 1.25 times this big. So this analysis tells me that if I have a tank that's 2520 cubic meters, that it will fill through the night, and then the tank is full of water. It's got 2520 cubic meters of water. And then through the day, it drains, and then it refills a little bit, but then it drains a lot at night, and then it goes down to 0 by the end of the 10 o'clock hour. But then at the beginning of the 11 o'clock hour, it starts to fill again. So in equals out, and we're good. The tank is large enough. So that's the procedure. If you didn't quite follow what I've just did in the spreadsheet, remember that this video will be posted on YouTube, and I'd be pleased to answer any questions. If you have any, just get in touch. But what we'll do now is we'll move on to talking about channel analysis a little bit more, specific energy and all that, unless there's just a quick question related to this spreadsheet before we move on. All right. You could do phase 3 of the project in less than an hour. You could do it in 30 minutes if you wanted to sit down and finish it tonight. All right, here is a picture of a bridge going over a river, and it looks like this is probably out west somewhere, just based on the mountains and the trees and all that. But the interesting thing is these piers that are in the river to help support the bridge, they are reducing the effective width of the channel. You've got a certain amount of water, a flow, Q, going through this river, but then when you put those the piers into the channel, at this location, the river isn't as wide because the water can't flow through the concrete, it has to flow around it. So the question we face in a situation like this is, how is the water going to behave when a channel is constricted because of a reduction of its width? Maybe we're making the channel narrower in a physical sense, or maybe there's some obstruction that's taking up some of the flow width. And so we're going to go through the specific energy analysis to address this question: does the water go up or does the water go down? And if you just went from an instinctual basis, you may think, well, if you're reducing the flow width, then maybe that's clogging the channel and so the water's getting deeper. And it can. It all depends on whether flow conditions are supercritical and subcritical, and so we actually have to run the numbers to find out whether it'll get deeper or shallower, and then by how much. We don't know until we do the calculations, and it's based on specific energy analysis. In a previous class on Wednesday, we looked at the specific energy diagram when you change the width of a channel. And when the channel width decreases, so B, lowercase b, remember, means the channel width at the bottom. If you have a certain amount of flow, Q, and now there's less width of the channel, then lowercase q, the flow per unit width, increases. And so that means that the critical depth will be higher, and The critical depth being larger means that the specific energy at the minimum is larger than it was before. And so here's curve 1, which was when the channel was wide. If you make the channel narrower, then that shifts the specific energy diagram up and to the right. So that's what we talked about before. So if you have specific energy that's gone up and to the right, then that's going to adjust the flow depth for a certain specific energy that's in the channel. So if you had supercritical conditions, then that would have one effect. If you have subcritical conditions, that would have another. Here in this illustration, this is saying if you had an upstream depth that was subcritical before, for a certain amount of specific energy, you have to go down to hit that new specific energy diagram, and that would decrease the depth. Even though the channel got less wide, we're constricting the channel, that's making the flow velocity go up so that the depth is decreasing. So it depends on the initial conditions upstream. So we're just going to, in the available time that's remaining, work through an example that's similar to what we did last time. Like in Wednesday's class, we said that the channel's physical width decreased. That's one way that we can have a constriction. Another is if these piers go into the channel. So upstream, before there's any constriction, we have a 2.5 meter wide rectangular channel and a given flow depth of 0.9 meters, and we're sending 2.25 cubic meters per second through that channel. So that's the flow rate. We could calculate the flow per unit width because we know B. And then downstream, if we needed to put a bridge over the channel and there's a couple of supports. So this text is saying that each of these supports has a width of 0.25 meters. So think, the channel's physical width is still 2.5 meters, but the effective flow width is going to be reduced because the water can't go through the pier, it has to go around the pier. And so lowercase b is less than it was before. So we want to know what's going to happen to the flow depth when that channel effectively is narrower than it was before because of the piers going in. We'll assume that there's no head loss, and so the C value that we could add to some specific energy analysis, we're just going to neglect that, and we'll say that the specific energy at 1 is equal to the specific energy at 2. And there's no bed step here, so there isn't a delta Z we have to worry about. It's just energy is being exchanged. There's going to be a different distribution in how much of the specific energy is as depth and how much of it is as velocity head. Okay, so what I'd like you to do is find out what will be the new depth. You see these question marks here? That means we don't know the depth. It used to be 0.9 meters beforehand, but the steps that I suggest you go through is, first of all, find the velocity at 1, because we know Q and we know A, so you can find the velocity and find the specific energy at 1. Specific energy is the depth, y, plus the velocity head. And then find y2 by setting the specific energy at 1 equal to the specific energy at 2. And let me just remind you the different kind of ways that we can see specific energy. We can have specific energy being in terms of flow rate, Q, so this is one way that we can write the velocity head, or we can have it in terms of flow per unit width at 2. Alright, so in this example that we're looking at now, we don't know the Y2, the downstream depth. We do know the flow rate Q, that's available. So what we can do is the only unknown, once we find E1 on the left-hand side of the equation, the only unknown on the right-hand side of the equation is going to be Y2. Okay, so let me pause for a moment and allow you to start thinking in terms of specific energy. I'll put you into the breakout groups in case you want to check answers and chat amongst yourselves, and I'll circulate among those just to address any questions that may come up. We'll take about 8 or 9 minutes and then come back together to look at the solution. Okay, welcome back from the breakout groups. I'm afraid that we may have lost some people when I pushed you to the breakout groups. It looks like maybe a couple of the people got disconnected. All right, so what we do is find the amount of specific energy at 1 and equate that to how much there is at 2. I found the critical depth just to determine that the flow conditions at 1 are subcritical, because our initial depth at 1 is 0.9, and since that's deeper than the critical depth, that means we have subcritical conditions upstream. So there's 0.951 meters of specific energy upstream, and we're going to say all of that goes into the specific energy downstream after the constriction, and it's going to be distributed between the depth and the velocity head. And the unknown depth occurs both in the y2 term and in the area term, which is down in the denominator. So we rearrange that into our cubic equation and find 3 roots, 3 solutions to that equation. We reject the negative root. The supercritical depth doesn't apply because we had subcritical conditions at 1. Remember, by comparing the depth to the critical depth, or we could have checked the Froude number upstream. Either way, it tells us that the new depth is going to be 0.865 meters at the constriction.